So, so today we'll finish off talking about how to get distribution coefficient from reference table characteristics of fluids to be able to talk about retardation attenuation. And next time we'll talk about vapor transport in the unsaturated zone, and that's basically us until spring break. And then after spring break we'll spend one period talking about modeling very quickly, and then we'll spend 3 periods talking about site investigation methods to be able to recover the information that you need to do the kinds of examples that you've been doing. Where does that information come from? How do you know what concentrations are? How do you know what the distribution of the free product is? How do you get the architecture of this layered plume in the subsurface? By drilling and by geophysics, basically. So those are the things we'll talk about. So, what we'll do. So you remember we talked about these terms here are defined in terms of a retardation coefficient. Retardation coefficient is equal to 1 plus the bulk density of the aquifer divided by the volumetric moisture content and the distribution coefficient, which we called it. And this expression we talked about last time is important because what we do with it is we can take our advection dispersion equation, accumulation term, dispersion term, advection term. They all have these components in them. Once we allow for retardation to occur, we end up with a term on the right-hand side, which is this retardation coefficient, which is always greater than 1 and less than infinity. And if we want to then, this accounts for these two processes, retardation moving slower through the aquifer than it would do if it wasn't sorbing, and attenuation being sorbed onto the aquifer, so it's actually in less concentration in the waterborne phase, which is of course the part that you sample if you're taking drinking water out, and therefore we want to know what those effects are. And so very simply, when we change the advection equation around, we get this red term to get the retardation, divide through both sides by retardation factor, so this becomes 1, and then it tells us exactly what the behavior is going to be in a straightforward way. It tells us that first of all, the advection part is going to be slowed by a certain amount. So instead of breaking through at the velocity times time, or at a length equal to the velocity times time, it's divided through by the retardation coefficient. So it's delayed by some amount bigger than 1. And if we look at the residence time distribution curve, the arrival, then it will arrive later. And it will arrive later by the magnitude of the retardation coefficient. And you can pull that directly out of this. We noted that this curve tends to sharpen, get steeper, as well as being delayed, which is curious. And you can rationalize that because this is reducing the dispersion in this relationship. And I guess we also made the point that the Peclet number, which is velocity times length over dispersion, and the pore volume or Courant number, which was equal to the velocity times time over the length. So the length is the length of our core. This is the arrival downstream, so this is when it occurs in the residence time distribution. And so our reason for doing that was that if you take the dispersion and divide by retardation, and the velocity and divide by retardation, then you get V over R and D over R. So that doesn't change this. but the pore volumes, you get V over R, and so this becomes advective velocity time R times L, which is essentially this term here, right? When this is equal to 1, it's broken through. So that's this term. So the retardation really only affects this pore volume term. It cancels out top and bottom on the Peclet number, so it doesn't affect it. And so the importance of that are that if we want to, we can just use these modified Peclet numbers and pore volume numbers modified with retardation coefficient, and we can do equatio with them, right? Remember we played around with those last time using these, not last time, time before, in working out these solutions, plugging these numbers into these closed form solutions. Long time ago now. We could throw it into here, this one in particular. We could throw it into this, and now they're just our modified ones for this one now has retardation included. So TR would be what we just said. What was it equal to? Velocity times length over velocity times time over length times retardation, I think, right? Suppose you can check the units. The units are meters per second, meters, seconds, nothing. So yeah, so it does cancel out. So it doesn't mean it is the right form, but I think it is. So that's the importance. So the important, I think, for this class is that you understand what physically the retardation does to the travel downstream, which is embodied in this. And I guess the other effect, which is shown in this little figure, is that this concentration peak might not be at a relative concentration of 1. It might be lower. And you can rationalize that is because it's getting sorbed, it's taken out of the material, the flow system, and plastered onto the solid, and therefore it's not present in the water anymore. So if you're removing it from the water, then you'd expect the concentration maybe to go down. So this might go down some small amount. So those are the effects. So that's a summary of what we've talked about. So what we'd like to do today is realize that this retardation factor depends on something called a distribution coefficient. And we like to know exactly how we might get that if, for instance, we don't have the convenience of having a natural gradient tracer test to be able to look at the difference in how far it travels downwind in a given time, which gives us our retardation directly from the two velocities, which we can get from the time traveled in a given, the distance traveled in a given time. So this is the question. How do we get KD, K sub D, from going to the library, basically? And so what we find is that KD is related to is equal to an organic carbon partition coefficient and a fraction of organic carbon. And so if we assume that all of the sorption in the aquifer is due to carbon, organic carbon, which is not true always, unless there's lots of organic carbon, then we can approximate the distribution coefficient by the organic carbon partition coefficient and how much the fraction of organic carbon there is as a weight fraction of the reservoir. And if that's the case, then we can use two metrics to do that. One is using the octanol water partition coefficient, and one is using the solubility of that substance in water, each of which are defined terms, which you can get from the library. And so this is all written down as we go down here. So you've got that, hopefully. So the idea is this. we can look at, what's this? Problem is solubilities are pretty low. This is 805 parts per million. Drinking water standards are even lower, 5 parts per billion. And so the solubilized part is at high enough concentrations to be a problem. And so that's the basis of wanting to be able to understand what the concentrations are downstream. So we can define 2 limits in behavior. If the amount of carbon in our aquifer is big, larger than 1,000th by weight, 0.1%, then we can use the expression that I just mentioned and get the distribution coefficient, which is what we want, from the organic carbon partition coefficient multiplied by the fraction of carbon. So this would be a decimal, not a percentage. So if it's so 0.1% is actually 0.001, of course, right? But the caveat is, and probably important, is that if the fraction of carbon is less than this, then using this method to calculate the distribution coefficient will massively overestimate it, massively underestimate it. Because if the organic carbon goes to 0, then this estimate would say that the KD is 0, and there would be no retardation in the aquifer. But some of the material gets sorbed onto the quartz grains. And if you don't allow for that by using these equations when the organic carbon is small, then it will give you the wrong result. So that's the caveat. There are 2 ways to get it using both of those terms. One is and they're all empirical formulae. And so if we know how much organic carbon we have in our aquifer, which we typically do, we want to know exactly what this is, the organic carbon partition coefficient, to estimate this, which is what we want. And we can use empirical relationships which define the organic carbon partition coefficient as a function of the octanol water partition coefficient, which I guess is the amount of octanol dissolved in water as a function of temperature, I suppose. And also define the organic carbon partition coefficient as a function of the solubility of that component in water, where water is a solvent, and I guess TCE is the solute dissolved in water. And so we'll just do 2 examples to do that. They both come from Feder. It's probably the most messiest slide in all of my slides. But if you go to Feder, which I know many of you, perhaps all of you, do not have, you'll see that there are many tables or empirical relationships which link solubility, for example, to the organic partition coefficient. And so that if you know the value of the solubility of a particular species that's dissolved in water, then you can calculate the organic carbon partition coefficient. And then if you can do that, you can calculate KD from it. And if you can calculate KD, you can get retardation coefficient, which is 1 plus bulk density of the aquifer, volumetric moisture content, distribution coefficient. And then if you have this, I can't go up here, but you know what this is going to. This is going up to our first page. If you know what retardation coefficient is, you can do all the gymnastics we talked about, transport downstream. So that's kind of the solution method. Okay? So this is the deal. So for ethyl benzene, not very clear, but the working is on the left-hand side. I'll switch to red. So you pick an appropriate formula. You know the log solubility. The solubility is equal to 140 milligrams per liter for ethyl benzene. You pick an expression, which is this one here. You have the solubility is equal to 140, and these relationships are not dimensionally homogeneous. You have to use the right units, so beware of that. This is in milligrams per liter. So the log of 140 is just a bit more than 2, right? Log 100 is 2, log 1,000 is 3. So it's, if you take the log of it, it's 2.15. If you throw the log of S into this expression, which is right here, 2.15 times 0.55 subtracted from 3.64, that gives you the log of the octanol organic carbon partition coefficient. You end up with 2.46. You 10 to the exit. Right. So 10 to the power 2.46 is equal to something bigger than 100, less than 1,000. It's equal to 288, and it's in liters per kilogram or milliliters per gram. So you have to be careful on the units. So we can get the organic carbon partition coefficient. And so if we have that, if we want to calculate KD, we just multiply KOC times F, fraction of organic carbon. This is no units. This is units of milliliters per gram. So this also will be milliliters per gram in terms of units. Okay, so it's just a formula. So that happens to be one formula. We can also do it in terms of, instead of solubility, octanol water partition coefficient. So if we do that here, again, the equations are specific to different compounds, but here we're taking a value, taking this expression here. If you can't see it, KOC is equal to 0.63 KOW. Oh yeah. So this is log KOW for benzene, which is this. The expression we're using is, we need, if we have the log, we have to take 10 to the x of it. And so this will be somewhere between 1,000 and 100, right? So 10 to the 2.13 is equal to 135, which is what this is. Put 135 into this expression that we had here, and you get KOC is equal to 84.98, or log KOC is equal to this. We need this value, right? We need KOC. And again, we can get distribution coefficient is equal to K, not log KOC, times fraction of organic carbon. If we know what this is, we know what this is, and then we have this, KD. And then the rest is just substitution in substituting this into the retardation coefficient to be able to use it. Okay, so just a recipe. So once we have each of these, we have this, and therefore we have our distribution coefficient. If we have our distribution coefficient, we can calculate retardation. And so the only thing we have to be mindful of is this caveat of the percentages, right? Stretching? Asking. They're prescribed. They're prescribed for those equations. You have to use those units.
They're empirically written such that when you plug in solubility in milligrams per liter, it's going to give you a value of
yes.
milliliters per gram.
Yes. Yeah. They're not dimensionally homogeneous. So, what was I saying? So yeah, so the caveat is you can only use them if there's enough organic carbon in the aquifer. So what we could do is we could try using that with the Borden data. The two clouds going downstream that were sampled, both with chloride ion and with carbon tetrachloride. So you remember when we talked last time about retardation at Borden? We said that if you have a cocktail that you release that includes chloride, sodium chloride, dissolved ion would be chloride, carbon tetrachloride and PCE. If you look after 2 years to see how far things have gone, the conservative plume has gone 57 meters, carbon tet's gone 23.5, and PCE's gone 13. And so we could use that to calculate the retardation coefficient, because we know just by looking at the lengths traveled, the relative velocities of the two components, you can take the velocity of the conservative species, and that is equal to a length traveled in a given time. You can look at the velocity of the non-conservative, that's a length traveled in a given time, sample it at the same time, and it's just the ratio of the lengths. And so we did that to get the retardation coefficients. Once we had the retardation coefficients, we could change this equation around to get Kd as a function of retardation coefficient, and we got that. And for carbon tetrachloride, I guess our retardation coefficient was 0.213 milliliters per gram. So we got that. So this presumably is a real number because it's taken from a real aquifer and is representative of all the processes that are going on. And also it's a gradient, a natural gradient experiment where it's moving at the in situ gradient, not being pumped. And so we might expect it to be quite representative. If we do the same calculation from Borden and do it for the actual fraction of organic carbon. So you'll see that this fraction of organic carbon is actually less than 0.1%. Not by much, by a factor of 5, I suppose, right? This is 20% of 0.1%. So if we try using this equation, solubility of carbon tetrachloride is 805 milligrams a liter. If we throw that into the relationship we had before by taking the log of this is going to be less than 3, but closer to 3 than 2, right? So it's actually 2.9, log of 805. And if you go through with that, then the log of the organic carbon coefficient is 2.04. If you tend to the 2.04, that is this. So yes, you have to be careful with your units, as I have been maybe in my past. So if you get that from this aquifer, the organic carbon partition coefficient is 110 milliliters per gram. If you take 110 and multiply it by 0.02%, which is 0.0002, right? It's as a fraction, or a decimal rather, then the value you get for Kd is equal to 0.02 milliliters per gram. If you look at the data from Borden, I thought I said it was 0.24, not 2.4. Yeah, okay, this is Kd. Yeah, okay, Kd. So if you can compare it, yeah, so this is the one calculated from Borden. So this is the one that was on that previous slide. And so you see that one is 10 times larger than the other. And so the question comes, presumably this is the right one because it was done at large scale and under natural gradient. And this one is actually 10 times larger than the one for carbon. And the reason is that if you had zero, this is the amount of carbon that's in the aquifer, which is very small, which is less than our threshold. You're assuming for this that all absorption occurs onto carbon only, none onto the faces of the quartz, and therefore this drastically underestimates the amount of retardation there should be in the aquifer. And so it underestimates it by a factor of 10. And so you can't use it for that reason. Okay? Sense? Makes sense? Yeah. All right. Yeah, okay. Hit me.
This might be stupid, but how do you...
Yes, yes it is, yeah.
How do you calculate the KD if it was at less than 0.1% case? You might be doing that.
Measure it in the aquifer.
You're just going to measure it?
As we did at Borden. Or I guess you could do it in the lab as well. You'd need to know how much absorption occurs onto the grains. You need, well, yeah, we talked about it, right? So we said that before, the one way that you could get KD, if I draw it here, is that you take, that's a good question. So, remember we said that you take a sample and you'd pour in something at a concentration C and you'd measure C star on here. And so you do that for one data point. Concentration in the water, concentration on the solid, which is removed from the water. You do it once.
You're going to create the absorption necessary.
Yeah.
And get the slope of that. That's all.
Yep. So you're going to get, it's basically KD, right? KD is, K sub D is C star over C. Yeah. So you use the isotherm. I guess that was my short answer. Would have been a shorter answer. Yeah. If you look at values for these retardation coefficients, so now a retardation coefficient for Borden was just a little bit bigger for that particular compound, 2.5. This is a bad slide, but these are a whole bunch of hazardous waste sites around the world. Borden is the one we just looked at. And I think the only important thing is to note that these values change with the compounds. So for one aquifer, with the same amount of organic carbon in it and the same characteristics of the quartz, these values vary. And they're between 2 and 10, I guess, 9 here, depending on different compounds. For different sites, they vary in different ways. This site here is a landfill in Gloucester, Ontario, and it matters whether you do a forced gradient experiment or a natural gradient experiment, but not by very much. They're roughly the same values. You can imagine measuring it in different ways. And I guess the other data point to pull from this is that the biggest numbers, I think the biggest number on this chart is of the order of 30. So it can be going 30 times slower than if you assume that it's going at the advective velocity. So a nasty, dirty chart, but gives you some appreciation of what's going on. Okay? What else? The other thing that I didn't mention was that we can write advection diffusion equation for one component I guess we could call it lowercase I. But if, like at Borden, you have chloride ion and carbon tetrachloride and PCE all part of the cocktail, then you'd have concentration 1 might be chloride, concentration 2 might be carbon tet, and concentration 3 might be PCE or whatever. And you can keep on going down from that. And so what you'd have would be, if you want to solve for this, you'd have three different equations that you're solving individually. These don't really interact with each other in a way to react with each other. So you'd end up with three potential curves representing what's going on downstream. And so these potential curves might have different retardation factors. Which means that your downstream arrivals, you might have three different curves. So in the aquifer, maybe you have, if you take a snapshot in time and look at what's going on, you might have curves that look like this, this, and this. Could be, this would have to be 1, right? If this is chloride, this is 2, and this is 3. So this is looking along the core, the same as this figure here. And this is C over C0. Or actually concentration, not C0. So the point is two things. One is that the retardation factors can change as it goes downstream. But the second thing is that the beginning concentration might be different because the solubility of these components might be at different concentrations for different compounds. And so you can certainly use this expression to be able to follow those separate three species downstream that each have different values of retardation coefficient and that have different values of initial solubilities, I guess. The solubility of chloride, the solubility of carbon tetrachloride, and the solubility of PCE. Right? And so we know how to get the retardation factors for those, for different compounds, because we just talked about that. And actually the Borden data were actually doing that also, right? These were for different compounds, so these are different retardation factors. But we haven't said anything about how we get these different initial solubilities. And so you might think that these values here would actually be the solubility of compound 2 and the solubility of compound 1 and the solubility of compound 3. In other words, if you put that compound in a beaker and leave it to sit, that's the maximum solubility that it would take up, and then it would sit there. But the maximum solubilities are not necessarily the effective solubilities which we need to be able to use this. So we need to convert from the maximum solubilities to what the effective solubilities are. And you must have had Raoult's law, right, somewhere in your past? Yes? Yeah, fine. So that just says that solutes will compete within the solvent for spaces within that solvent, and you can get the effective solubility of that compound by knowing the mole fraction of that free phase component and its solubility. And so this is the value you take out the reference table, the absolute solubility when there's only that compound in water, for our case. And if you know what this is and you know the mole fraction in the D-NAPL or the L-NAPL, then you can calculate its effective solubility. And so this calculation is just to do that for Borden. So you're familiar with these, not Borden, for Smithville. So you're familiar with the proportions of TCE, TCB, and PCBs in those, and mineral oils, I guess. Those are the four compounds. The weight percents were 2%, 10%, 50%, and 38%, I guess. They sum to 100. If you know the formula weights for each of these compounds, then you can calculate the amounts of these. So if you have 2% by weight and the formula weight is 131, then it's 2% over 131, or 2 100ths over 131, at least in the proportion. This would be 10 over 181, etc. And then this would be 50 over 220. So this is the actual masses of these that are present, or the moles per 100 grams of cocktail. And so if you sum up these, this is the total number of moles in the system. So this is just the sum of these. So the moles per 100 grams is 0.015. Moles per 100 grams is this. Add them all together, this is the total number of moles. If that's the total number of moles, then you can divide those moles by the total number of moles to get a mole fraction. So the mole fraction would be the number of moles divided by the total number of moles. So 0.0152 divided by the total number of moles. This is 77. And it comes out to be almost the same as by weight percent, but not quite. 2.2. The solubility of TCE is 1060 parts per million, milligrams per liter. If you multiply 1060 by 0.022, then you get the number that you can't see here, which is 2.23, roughly. And you do that for the others. You, instead of being 10% by weight, it's 8.8% by molar content, and that gives you the amount, the solubility of these. And so if you were plotting, for instance, the behavior of this as it goes downstream, then for TCE, this would be 23, I guess it's milligrams per liter, so it's ppm. So milligrams is 1,000th of a kilogram, 1 kilogram in a liter, 1,000 grams in a kilogram, so it's 10 to the 6, so it's part per million. And if you're doing it for TCB, I think it's 1.5. So the down gradient distribution would look something like that if you took a picture of the core. And I guess whether you're here or here depends on the relative retardation factors for the two compounds. I don't know what those retardation factors are because we haven't done it here. But the start, all to say that the starting concentration, when you're looking at it moving downstream, would start off at this effective solubility, this value here. And that's all we've calculated in this rightmost column, the effective solubility. So we need to know we have the weight fraction, we need to convert that to a mole fraction. We need to know what the solubility is, and if we have that, we have enough to calculate that. And if we have that, and we know what the retardation is, we can calculate exactly what the plume will look like as it goes down gradient. Okay? Not so straightforward, but not rocket science either. Okay. Not going to talk about that. You've already done some calculations. So presumably, if we know the mass that we have, whoops, and we know the mass rate of removal, think you've used this already. That equals the time, right? This is mass per unit time. So one divide the other will give you seconds or years. And so if you know the amount of mass that's present in the system and you know its rate of removal, you can calculate how long it would take to remove it, which might be a useful number if you're doing it by dissolution. I guess you also know that the mass rate of removal is equal to the volumetric flow rate times the solubility, I suppose, effective solubility. So this is a volume per unit time. This is a mass per unit volume, and therefore this is in kilograms per second, mass per unit time. And so if we know the rate at which you remove it, you could calculate how long it takes to remove the complete amount. So I guess that's what's written down here. We can also write it in terms of the mass, which is, I guess, what I used uppercase M for. The velocity, so these two terms together. Exactly the same thing, right? If you take these two terms and combine them. So advective velocity times porosity equals Darcy velocity times area. This totally equals Q. Saying exactly the same thing, right? So these red underlined components represent the volumetric flow rate, the concentration, the effective solubility, and the product of those will give you the mass removal rate. So that's what. And so you've done this already, so perhaps I won't belabor it. So if you know the velocity at which something's going through it, you know effective porosity, you know cross-sectional area of flow, if you know how much mass you have in the system, and you know what the concentration is that you dissolve it at, you could use all these together to be able to calculate how long it takes to come out. And if you do that for some numbers for a sandy soil with a hydraulic conductivity of 10 to the minus 3 centimeters a second, hydraulic gradient, this is dH/dx, of about 1/100, porosity of 30%. I think the residual amounts were 30 liters per meter. Yeah, it doesn't matter. The only point in doing that calculation is that when you calculate how long it takes to remove that material, it's actually a very long time. And the reason is, not surprisingly, because you're moving at very low concentrations. You're moving at the solubility, I don't know what we've used here, PCE. The solubility is 200 milligrams per liter. Just keep on wanting to do that. Solubility of PCE is 200 milligrams per liter, 200 parts per million. So I've arbitrarily used 10%. Don't worry about that now. If you use this amount here, it would take 74.4 years. It would scale directly, right? Because it would take it out 10 times faster. But the point is it takes a long time to be dissolved. So dissolution is a method of remediating sites unless it's natural remediation, just by flowing through it, is not really a viable way to cause remediation. So you've done that calculation. You could think about a different calculation. So you could think about two different forms of these pools. And so we had drawn this chimney idea, right? I like using this. And I guess with a bit of artistic license, we also used this and this, etc. So what we've talked about here is the fuchsia behavior, right? You're flowing water through a block, and that block perhaps looks like this. And is really exactly what this is, going from upstream to downstream. It's distributed in here, it's a smear, it's flowing through here basically at the same velocity it would be if there wasn't residual NAPL there, perhaps slightly slower, but roughly the same. But it doesn't account for the behavior that you have either with these lenses, and certainly not with the puddle or the lens that you have at depth. And so this isn't distributed at all, and so you might want to know exactly how this would pick up components as it flows past. And so the other geometry that we might want to use is a geometry that looks like that puddle, a penny that's submerged in the aquifer, that has a height which is HP. P is for the puddle, if you like, this underground puddle. And you can imagine that as water flows past it, maybe just on the top, maybe top and bottom, that this is just diffusing by Fick's law into the flow field, gets picked up by the flow field, and then gets carried downstream. And so what we could use is we could use a solution that accounts for diffusion from this surface into the porous medium, into the, I guess, the y direction in this case. And there's a solution for that. And it gives the mass averaged, mass transfer rate, M sub A, averaged per unit area of this top surface. And this is this, MA. It's a function of the dispersion coefficient. Remember, dV is equal to molecular diffusion coefficient plus alpha times advective velocity, right? This is our longitudinal dispersion coefficient, which is equal to the length of the plume divided by 10, perhaps. We talked about it. And for the reasons that we said, it's not really related to the porous medium, but the scale of the plume. This is the advective velocity. This is the diameter of the penny, if you like. And this is the solubility. This is the saturated, the maximum concentration, and the effective porosity. So this is dV, which we've just described here, and all those terms. And so now, if you want to calculate the time taken to remove the material, then it's given by the mass rate of removal, which is this. I suppose we could check that the mass rate of removal has the right dimensions. It's going to be diffusion coefficient. So this is length times length over time. So this is meters squared per second. This is a velocity per second. And 1 over meters to the half, which is meters per second, I think, right? Meters squared per second squared square root multiplied by kilograms per meter cubed multiplied by something. So this is in kilograms per second, meters per meters cubed, which is equal to mass per unit time per area, 1 over area. So it's mass per unit time per area. That's what we're saying. So that for each little area we have on here, little differential area, this is the amount of mass that comes off this. And so what we're doing is calculating here within this. Oh, didn't want. Oh. So this is a unit area. So the time taken to remove it is equal to, I guess we called it HP before, and I've called it pH, right? This is HP. Times porosity. So HP times density times porosity times saturation. So porosity times saturation is the proportion of the volume that's filled with NAPL. Porosity is a pore space. Only a part of the pore space is filled with NAPL. Multiplied by the density of that, and the height gives the amount that's in a column that's going through here, I guess, right? So the volume of this column is equal to HP times 1 times 1. And so the volume of the NAPL is equal to volume times porosity times solubility. Not solubility, saturation. Right. Residual saturation of the NAPL and its porosity is the amount of the pore space that's filled up with NAPL. The height, the 1 by 1 meter. So this whole term here would be the volume of the NAPL. Per unit area times the height. Yeah. This as well. Making a pig's breakfast of this, I see. Never mind. Those two terms together give you the volume. And if you multiply the volume by density, it gives you a mass. And if you divide this whole thing by mass rate of removal, this term here, then by definition it gives you a time. So the equations are right. Bad explanation, but the equations are correct. So if we know how much we have in place, and we know the rate at which it's being removed, we can calculate how long it takes. Arbitrarily before, I used to remove that. Is this not working? Remove that. We used before a value for the solubility which was only 10% of the actual solubility for a single phase. And we didn't really explain that. And the explanation for that is if you look at results from experiments that are trying doing exactly what we've talked about doing. So you take an aquarium, you fill it with sand, or you take an aquarium, you fill it with a pool of TCE, and you dump sand on top of it, and you fill it with water. And then you flow from upstream to downstream. And then you measure the concentrations that you remove fluid from at the downstream side. If it's TCE, and its solubility, if there's only one component in there, would be 1,000 parts per million, milligrams per liter. If you look at the relative concentrations when it comes out, if you change the velocity that it flows across the tank, increasing from a small value to a larger value, you only get something like 10% of the actual concentration, even at 1 meter per day. If you increase it tenfold, it decreases it slightly, but the problem is that it doesn't spend enough time in contact to be able to take up a full load before it's washed downstream and out of the system. And so it's a lottery as to the magnitude of the concentration you take, because it may well be that it's not yet in equilibrium with the system. And so this will be the this is saturation, but the concentration that you end up using would be a maximum of the solubility, and it might be less than that. So solubility is a maximum, and it might be a lot less than that. 10% is a lot lower, and so you might need to adjust your results for that. And it's just because it doesn't spend enough time in contact to reach equilibrium. So lots of unknowns that we should be aware of. But the final thing that we should talk about before we split is, if you have this system and you have a block which you have that has some saturation in it, and you only know what the concentrations are, how do you calculate the total mass that you have within your aquifer? So we've talked about how you might do it by taking the volume, multiplying by the saturation and the porosity, but we haven't allowed for a different effect, and that is we haven't allowed for the amount that's going to be sorbed onto the system. So how do we calculate the total amount that's available if we only have the concentration? And so for a contaminated aquifer, which we could think about, these are silhouettes of the plan view of different contaminated waste sites in New Jersey, California. I guess Borden is not on there. And the question is, if you sample downstream to get the concentration in the water, which is a very easy experiment to do or measurement to take, how do you calculate then what the total mass that is present in this plume would be if you just have this value? Well, in theory, you could get the total mass by just having the total volume of the aquifer. So VT equals, I guess, total contaminated volume so it would be this area multiplied by the depth, right? So if you think of this as a plume, I guess it's probably coming from here, just from the shape of it. It's bifurcating. Plumes don't usually join. They come from a single source and they bifurcate. So if you knew what this area was and multiplied it by its depth, this is the amount of the aquifer that's contaminated. So this is the amount that's contaminated by dissolved components. So the total volume would be that. If you multiply the total volume by the porosity, this is the void volume. And if you multiply it by concentration, then you have the mass that's dissolved in it. Everyone leaving me? 2 seconds. But that doesn't include the amount that's sorbed onto the solid portion. You have to add an amount that's sorbed onto the solid, and that is the concentration that's sorbed onto the solid, the density of the aquifer, and again the volume of the aquifer. And if you use the definition of the distribution coefficient, which is the concentration on the solid divided by the concentration on the water, and you substitute for this, you end up with an incredibly simple relationship which says that the total dissolved mass, including the amount that's sorbed onto the solid part, is equal to the concentration, porosity, and the volume, which is what you might have used, but post-multiplied by the retardation coefficient. Retardation coefficient is always greater than 1, so there will always be more than just the dissolved amount, and you can calculate it. And the final statement I'll make is that if you look at these different infamous field sites, you get a huge plume volume. You know what the concentration in that plume is, but it turns out to be not very much volume of spilled component. So these are barrels, oil barrels, 70 drums. So some of them can be a tiny amount of contaminant, but because it spreads out to very low concentrations, it can fill a very big volume of your aquifer, which then is a very big volume for you to clean up. So that's it.